So we're going to continue talking about work, and in this video we're going to focus on situations where there's multiple forces acting and affecting the amount of work done, and some of them are at angles, and we'll kind of see how that all factors in. And so we know so far that work is equal to the change in kinetic energy, okay? And when you think about the total work done on an object, then we think about, like, just like we have a net force, we can have the net work done, which is basically the sum of the work done by all the forces. And so you could add up the work done by, say, like, there's 4 forces. You could add the work done by all 4 forces, or you could find the net force and multiply that by the displacement to find the total work. Okay, and these two methods are equivalent, and it's totally up to you how you want to use them. Okay, so in this example we could use either of those methods. We'll just use the one in which we find the work done by each force individually. So we have this object with a mass of 3 kilograms. We have a 30 Newton force pulling it up at an angle, so it's kind of being pulled along this horizontal surface. Let's say it starts from rest and that it's been dragged. Maybe we want to find out how fast it's moving, maybe after 2 meters. Or let's change it up. So let's say that in this case it's dragged some distance, and at the end of that distance it's going 3 meters per second. So the question is, how far was it dragged? Okay? And so based on this question being asked, it probably makes more sense to find the net work done so that we only have to multiply displacement once, okay, or the net force, and then multiply by displacement to find work instead of find the work done by each individual force. Okay, but actually I'm going to go ahead and do it the other way just so you could see it. Okay, so let's start with a free body diagram. And so we have the weight, we have the normal force balancing it out, we have some friction pulling back, we have a coefficient of, we'll say, kinetic friction of 0.3, and then we have it pulled up at an angle with a force of 30 newtons. So if I want to find the total work done, I'm going to find the work done by each of these forces, remembering that the definition of work is the force times the parallel displacement, or F times delta x times cosine of the angle between them. Okay, so we'll go through each force. So we'll start with this pull of 30 newtons. So we'll say, okay, so for that one, it's 30 newtons times the cosine of the angle between that and the displacement. They have a displacement of delta x. And then if we look at friction, well, let's do the weight now. So we have the weight times the displacement times the cosine of the angle between them. In this case, if the displacement is this way right here, the angle between the displacement and the weight is 90 degrees, so it'd be cosine of 90. We'll do the same for the normal force. That will also be 90 degrees. And then for friction, remember that friction is mu times the normal force. In this case, the normal force is equal to the weight, so times mg. And again, times the cosine of the angle between the force and the displacement. So this would be times displacement times cosine of 180. Okay, so when we work this out, this becomes 0, and this becomes 0 because cosine of 90 is 0. And in this case, this cosine of 180 turns into negative 1. And so when we simplify all this, we get that the total work is equal to this piece minus that piece. So once we simplify that, we get 28.2 times delta x minus 8.82 is equal to the total work, which is equal to the change in kinetic energy. So we're going to say 19.4 times delta x is equal to the change in kinetic energy, which would be 1/2 times the mass of 3 kilograms times 3 meters per second, which will square, minus 0, which will square. And then we can go ahead and solve this to find displacement. So we find that displacement is going to be equal to about 0.7 meters. So that means that if this scenario was happening by the time it had been dragged 70 centimeters about, it would be traveling 3 meters per second. Okay, we'll do one last example. Let's say that we are pushing a broom, so we're sweeping. This is like one of those big push brooms. And we're pushing it at an angle of 40 degrees, and we're pushing it at a constant speed. Okay, I said this was 0.1 kilograms, probably closer to 0.5 kilograms. Okay, and so let's say that I want to know what, let's say I'm pushing with 30 newtons, and let's say I want to know what mu is. Okay, and so if I'm pushing it at a constant speed, that means that the change in kinetic energy is 0. So let's go ahead and draw a free body diagram. We have weight, we have a slightly decreased normal force, we have the push, or sorry, a slightly increased, it'd be bigger. Then we have the push inward of 30 newtons, that's 40 degrees below, and then we have friction. Okay? We know that the friction and this force right here are going to balance each other out. And actually, to simplify this, let's ask a different question. Let's say instead of finding coefficient of friction, let's change the question to be how much energy is going to be lost to heat when you push this broom. So the question is, how much energy will be lost to heat? And so what that's talking about is thermal energy. And thermal energy is energy that kind of vanishes from a system. And a really common way that we can create thermal energy is through friction. And so whenever friction occurs, friction takes energy away from something, and that energy doesn't go anywhere except to heat things up. And you can think about rubbing your hands together. Your hands get warm because the friction between your hands creates thermal energy. Okay, so the question is, how much thermal energy, or how much energy will be lost to heat? And so we can solve this using work. We can say, okay, the work done is equal to the change in kinetic energy. Okay, well, since it's going to maintain a constant speed, then the change in kinetic energy is 0 joules. Which means that the work done by the push plus the work done by friction, when we add those together, they'll be equal to 0. Okay? And now we can find the work done by the push by using the definition of the work, right? The work done by a force is the force times the displacement times the cosine of the angle between them. So in this case it would be 40. So I guess there's some information missing here though, because they didn't provide a displacement. So let's plug this in and we'll decide what the displacement will be. So we could say, okay, it's a force of 30 newtons. So we'll say 30 newtons times displacement times the cosine of 40 plus the work done by friction be equal to 0 joules. Okay? And then here we can say, let's say maybe it gets pushed, you push the broom for a meter. Okay? And so now we can solve for the work done by friction, or how much energy was lost here to heat, but just by simplifying.